Hello everyone, welcome to today's workshop in Advanced Physics in Unity. My name is Yang. I'll be representing the Gamers Union to bring you this workshop. So the goal for this workshop is to introduce you to some low-level concepts and considerations that make up a design of a physics engine. And we also want to show you some what kind of control the physics engine have over in the actual Unity game engine, and some of the limitations of the Unity physics engine and some of the ways that we can work around those limitations. And we're also going to get practical and introduce you to some best practices when working with physics in Unity. So I'd like to start with this little case study of when you move a physics object the quote-unquote wrong way. So in this scene, we have two red objects here, and they are supposed to be the walls, the static objects that cannot be moved and cannot be passed through. And this blue cube here will represent the player, or a dynamic physics object that cannot pass through any walls. But we're moving it the wrong way here. As you can see, the physics object just passed right through the wall. So by the end of the workshop, we're going to see how we can fix this case study. But let's start with the basics. What is a physics engine? Well, a physics engine is a system that is responsible for simulating the motions and reaction of objects in the game as if they were under the constraints of real-world physics. So they are responsible for gravity, forces, collision detection in the game. And we have this really nice animation to show us an example of a physics engine. So number one, which is the first one here on the left, is no physics, which just means that we don't apply any forces or physics simulation to it. Number two here, you can see that the object fall right through the platform. That is because we enabled gravity on that object, but we didn't enable collision detection on it. And for number three, we have the object fall is caught by the platform, so there is collision detection, but it doesn't react naturally to how a physics object would when it's falling. And number four is when we enable everything, gravity, collision detection, and rigid body dynamics, so that the object would react naturally to the forces around it. So this is a really nice example to demonstrate what a physics engine actually do in the context of a video game. And let's talk specifically about the physics in the Unity engine. So the rigid body component is the end-all be-all component when it comes to physics in Unity. It is the component that provides physics interaction, gravity, forces in Unity. And if you look closely, we have this checkbox here, is kinematic checkbox. So this checkbox is rather important, and I'd like to talk more about it. So what exactly does it do? Well, the is kinematic checkbox, if it is enabled, means that if the checkbox is checked, the object is no longer affected by gravity and forces. It becomes a static object. So as you can see in this animation here, the red cube is a dynamic object, which means that it's not a kinematic object. But the orange cube is a kinematic object. It stays still, is not affected by gravity. As you can see, it's not falling, and is not affected by the red cube, which falls on top of it. So why would you want to make an object, a physics object, kinematic? Well, this is a very good sort of way to make, say, walls or boundaries in your game where you don't want the player to cross it, you don't want the player to go through it, but you want it to interact with other physics objects. So, an example that I have here are the trees in Grand Theft Auto 5. They are kinematic objects, and we're actually gonna come back to Grand Theft Auto 5 with kinematic and physics in a case study that we'll do at the end of the workshop. It's quite interesting. And we also have colliders in Unity. So the collider component defines the shape of an object for the purpose of physical collisions. And what usually happens is that Unity can provide some basic collision shape, like a box, a cylinder, a sphere, but say you're using a 3D model in your game, and Unity don't have the specific shape of your model, as we can see, like the gun right here. So what usually happens is we use a rough approximation of the gun model using the provided shapes. Here we have cubes, another cube, another cube, another cube. This is a capsule. So we use all of these to provide a rough approximation of the mesh. So, and that is usually efficient and enough. And in gameplay, no one's actually gonna notice it. And also one very common but a common issue when it comes to physics in Unity is the concept of fixed update versus update. And so what are those? Well, they are both Unity event functions. So functions like start or update, fixed update, on enable, on disable, those are functions that are called by Unity itself. So you don't have to call these functions. They are called automatically, but they differ in when and how often they're called. So update is called once every frame, and it by default it will try to run as fast as possible. And say your game is running at 500 frames per second, then update will be called 500 times in 1 second. But what about fixed update? Well, fixed update is called every time the physics engine recalculates, and it will try to be consistent instead of run as fast as possible. So when you're using something like gravity or forces, the physics engine has to calculate the position of the object if you're using it. And the rate at which it recalculates is usually in Unity is every 0.2 second. So every 0.2 second fixed update will be called. And all of this just means that when you're using Unity, and especially when you're using physics in Unity, we should perform the physics operation like add the force, change in velocity, etc. in fixed update, and we do other calculations that require calculations every frame in update. And this is not just a problem in Unity, but also in other engines and other games as well. So we'd like to sort of expand it to a more general topic of physics update versus game update. So, comparing the two types of update. So we already talked about, physics update is how often the physics of the game are recalculated, like gravity, right? If something falls, the physics engine has to calculate the position of the object by by physics update. And game update is often how often the screen re-renders its content. And physics update also usually runs at a consistent fixed rate. And game update is unless otherwise specified, meaning that you can cap the frame rate of the game to something like 60 frames per second. But unless that is specifically stated, game update will run as fast as the hardware will allow it. And usually when we talk about fixed update, we use the unit hertz. And what it just means is the number of times is recalculated per 1 second. So the example I give here is the Unity's physics engine update at 50 hertz, meaning that the Unity's physics engine update 50 times per 1 second. And when it comes to game update, we're already familiar with the terms frames per second. And it's how many frames a game render per 1 second, 60, 30, 100 frames per second. And I have this really interesting case study about Crysis Remastered on the PC. And I'm gonna play the video, but essentially what happens is the plants, the vegetation, and the foliage, they actually only update at 30 hertz, while the game, as you can see on the right here, it looks very, very choppy and very weird compared to the left. Well, the game can be running at 100, 200 frames per second. So what happened there? Well, the explanation, I'm gonna play the video again so you guys can see. The explanation is that this is likely an artifact that was carried over from the Xbox 360 version of the game, which ran at 30 frames per second. So the physics update at 30 hertz or 30 times per second, and the game also ran at 30 frames per second. So it doesn't look as bad as we're looking at it here, but when they remaster it, they didn't fix it, and we run it on the PC with a much higher frame rate, but plans only update at 30 frames per second. So we have this, artifact here. And so another case study is also quite interesting. Is your frame rate actually determines how fast your gun fires in Fortnite and PUBG. The lower frame rates will bottleneck your how fast you fire. So if you look at the animation here on the right, is the game running at 300 frames per second, and the left is 30 frames per second, and you can see that it's slightly faster. You can fire slightly faster when you're running at 30 frames per second. And this is not significant when you look at it, but it gives people a competitive advantage. And the speculation for this is, because we don't actually know what happened here, the speculation is you can only fire a maximum of 1 bullet per frame. And in a high frame rate setup, this bullet can be fired over several frames. Well, in a low frame rate setup, this fire rate is bottlenecked. So say your gun's fire rate is 30 bullets per 1 second or more than that. In a low frame rate, you can't fire more than 30 bullets per 1 second. So that's how it's bottlenecked. Then let's talk about some collision physics in Unity. So remember the case study that we did at the beginning of an object moving through the wall? And this is the source code for it. It's very simple. We're moving the object using translate, moving to the right, times the velocity and time delta time. So what's the problem with this case study? Well, the problem is that we're moving a physics object by directly manipulating its position. So this leads to the physics system and the script actually fighting each other. So if the object runs at the wall here, the physics system will tell Unity that, will tell the object that, you hit a brick wall, don't go any further. But your script here in update is just gonna move to the right or move in this direction because it doesn't care. And in this case, the script wins because remember, update runs as fast as possible. So here it's actually running at like 200 frames per second. Well, fixed update or the physics calculation only runs at 50 times per 1 second. So this update wins outright. So what's the fix? Well, the fix is simple. First of all, we move the physics object using a rigid body instead of directly manipulating its position. And secondly, we move the logic into fixed update instead of update. And as you can see, the result, we're moving forward, and when we hit the wall, bam, we don't go through it anymore. Great. So non-collision physics is also actually quite an important topic, as we're going to see, especially in Unity. So raycasting, this is a very interesting topic. So what is raycasting? Well, raycasting is a technique where you shoot an invisible ray, or cast an invisible ray from the origin point at a direction. And we can then check which objects did this ray hit and do some interesting thing to it. So this is very sort of prominent technique in first-person shooters or any shooters for that matter, because every time you shoot a gun, raycasting is used to check which object did you hit or did you not hit. So this is a very common technique in that area. Similar to raycasting, we also have overlapping. So raycasting is we shoot an invisible ray. Well, overlapping is that we form an invisible sphere or box around an origin point. And again, we check any object is caught in that box, and we do things to it accordingly. So as you can see in the diagram here, the origin point, and we form the overlap, and the green objects are the one that is caught in the overlap, and the orange ones are the one that is not caught. And usually in games we use this to when we have an explosion or a grenade or something like that, and we want to check if any object was in the blast radius, and we deal damage to those objects accordingly. And we also have triggers. So triggers are actually colliders. They have the same sort of shape as the collider, but the difference is that they do not interact with the physics simulation. So when two colliders hit each other, they will react, not allowing them to pass through each other, but the trigger will allow you to pass through it. And the only thing they do is they document which object will have entered or exit the zone of the trigger. And these objects can be accessed through code. And a good example of using triggers in games is when you step into an invisible trigger and a cutscene starts. So we have this little example here of me walking through the game and stepping into an invisible trigger and trigger a cutscene. So I'm gonna let this play here. I'm walking, and boom, and a cutscene starts. So that's how most cutscenes are sort of triggered in games. The developer just place an invincible trigger in the area to check whether you've entered or exit the area. And so we have talked about the Unity physics engine, but what about some of the other physics engines that are used in the industry? Well, you might or might not have heard of PhysX. It's a very popular physics engine. If you start off like a lot of games, they have specifically a setting for PhysX. So it's used in the examples that I give here are Batman Arkham City, Borderlands 2, Mafia 2, but there's a lot of other games that use PhysX. Box 2D is a physics engine for 2D games, Shovel Knight, Happy Wheels, and a very physics-based game, Angry Birds. The Bullet physics library used by Arma and Metal Gear Solid, and finally we have the Havoc physics engine, which is also very popular. It is the physics engine that is responsible for the destruction system. It's a very impressive system in the Battlefield games. So the example I have here, Battlefield 4, I believe Battlefield 5 also use Havoc physics, Elder Scrolls 5, and Assassin's Creed Odyssey. And with that, we're going to talk about some interesting case studies of games that do interesting things with their physics. So, Human Fall Flat. This is a very interesting game, for me at least. So, usually in games, when you move around your character, the game move your character in the direction that you want, and it just usually play a running animation. Well, in Human Fall Flat, the ragdoll, your character, is actually a dynamic rigid body using a combination of ragdolls and rigid body physics, and it features dynamic movement like walking, grabbing, and climbing, and it likely takes advantage of Unity's inverse kinematic system to dynamically generate the movement of bones moving from point A to point B. And another game that we're also really interested in is Portal. So this is a very brief overview of how to make Portal in Unity, but essentially it contains two components, the visual and the actual interpretation. So the visual part, a non-primary camera is placed behind the portal and generate a texture, and then we can apply that texture onto the portal to essentially see what happens on the other side. And for the interpretation part, we just move the objects and clone the objects that are moved in the portal and just carefully position them to essentially fake the portal effect. And we also have this really interesting sort of comparison between hit scan and projectile weapons. So as you can see on the left animation here, every time the gun is fired, the object at the end of the gun or at the sort of range of the gun is immediately taking damage, right? Like right here. And this is called hit scan weapon because every time you fired, or every time the enemy fired, whichever object that is caught in the raycast, remember we talked about raycast earlier? Well, every time we pull the trigger, any object that's caught in the raycast immediately take damage. There's no way of avoiding that. But we also have projectile weapons on the right here. And projectile weapons, as you can just see, fire a slow moving object that has collision detection on it. And so every time it hits an object, maybe it will explode, or in this case it explodes, or do some interesting things. So projectile weapons usually like fireballs, rockets, etc. So we have these two distinctions in first-person shooters, but in recent shooters, collision detection of small, fast-moving objects is getting very, very accurate. So small, fast-moving, like a bullet. So we see more and more weapons in games that they technically fire projectiles, but these projectiles, let's go here. But these projectiles are so fast that they just might as well count as hit-scan weapons, because you can't actually try to avoid these projectiles. So the example I have here, Gears of War, you can see the projectiles and when they hit the target, but these projectiles are really small and really fast. So it's kind of projectile, but it's also kind of hit scan. It's kind of both. And finally, we have the case 3 about the train in Grand Theft Auto 5. So if you have not played or heard of this infamous train, so there is a mysterious train in Grand Theft Auto 5 that never stops. So a lot of players have tried to stop it by putting heavy dynamic objects in its way on the rail, like cars, planes. In this case, you can see a tank, but the train just keep going. So the question is, well, first of all, can you even stop the train? And second, why? Well, I'm only talking about like the base game here. No, I'm not talking about like mods to stop the train or anything. But in the base game, you cannot stop the train, no matter how hard you try. But why? Why can't you stop the train? Well, the explanation is that the train is actually a static object, that it doesn't adhere to any physics simulation, like a dynamic object. So it can still collide with other dynamic objects. So that's why everything that you put in its way goes flying. In this case, a bus. But the train is not a dynamic object. So we think about that example of trees earlier. When you ram into a tree, but it doesn't actually do anything. This is the exact same thing, but the train moves. Why is that? Well, the train, like the movement of the train, is not physics. It's hard-coded into the train itself to always move, never stops, and because it doesn't adhere to any sort of physics simulation at all. So we think of it as a moving brick wall. So that's why you cannot ever stop the train, no matter how hard you try. And we have here some resources for you to learn more about physics, and specifically physics in Unity in general. And that is the end of the workshop. Thank you everyone for tuning in. Have a great day.